Okay. Uh, Today I am starting this basic topology second part. Okay. Previously I have given you up to this Cantor theorem. So I have rescheduled this one. This has been done. Then partially ordered sets has been done. Schroeder-Bernstein theorem has been done. Cardinal numbers and cardinal arithmetic is done, but I am not satisfied as uh, there are many things, but I had to left. So Cantor theorem I have done. Today uh, I want to go further. That is in continuum hypothesis. Okay. There are many queries remain to be solved decisively in cardinal numbers. Okay. These are really uh, these are this uh, as we know that the cardinal number of Z, the set of whole numbers, and the Q, the set of rational numbers, have same sizes. But is there any set whose size is strictly bigger than Z but strictly lesser than Q? So the cardinal number of Z and Q are not same, but their size is same. So both the sets are strictly lesser than, and both the sets are strictly lesser than the real number set R. So these are the problems that have not yet solved. Okay. The so this question, the continuum hypothesis is something like that. It says that there is no set A with what is n0. N0 is the cardinal number of the natural number set. And what is C? C is the cardinal number of the set 0, 1. That is closed set 0, 1. So is there any cardinal number, a set whose cardinal number lies between these two? This is continuum hypothesis. Okay. It asserts that the first cardinal number C is the greater than n0. But can you prove it? You cannot prove. It cannot be proved. But whatever you go on thinking, or you go that it cannot be proved to be false also. But Kurt Gödel, he is the greatest mathematician, and so far as I know, that he is the greatest logician, showed that continuum hypothesis cannot be disproved. But in 1960, Paul Cohen showed that continuum hypothesis cannot be proved also. Cannot be proved that it is true or false. So this is a hypothesis. It has not yet been proved or proved. Either it is true or false, but it cannot be proved or disproved. Okay. So this is continuum hypothesis. And next one is John lemma. Now John lemma tells you that John lemma tells you about this. Let X be a non-empty subset, non-empty partially ordered. But what do you mean by partially ordered? Now you know, in which every totally ordered subset has an upper bound. Then what is upper bound? You know. Then X contains at least one maximum element. So this is John's lemma. Now why it is lemma? It is not a, because it cannot be proved also. So next slide. Uh, so this is John lemma. If you want to, you can learn it by heart, that every totally ordered subset of a non-empty set, partially ordered, but the subset must be totally ordered. It must have an upper bound. So this greater set has at least one maximal element, that means the least upper bound. Okay, now let S be a partially ordered set. If every totally ordered subset of S has an upper bound, then S contains a maximum element. That is the theorem of John's lemma. Now you have to understand, if you understand this theorem, you have to understand what is partially ordered set, what is totally ordered subset, what is upper bound, and what is maximal element. So partially ordered set, I have told you, just this is the recapitulation. Okay, it is a binary relation denoted by less than or equal to, which satisfies the following properties. So these properties all you know. When we fix a partial ordering, that means a set that is between any two elements, this relationship holds. Okay, we refer to S or pair, this pair, as a partially ordered sets. It is important to notice that we do not assume all points of the elements in S are comparable under this. For some S and S1, we may have neither this nor this. Okay, neither this nor this you may have. Okay, you may have neither this nor this. So uh, remember this fact. S1 is another set. S is here. There is a here it is. It will be S1. It will be S1. Okay. So let me correct it. It is here, but why it is not here? No, S1 nor S1 is less than this. If all pairs of elements can be compared, then we say a totally ordered set. Okay, so if between all the elements of the set S this relationship holds strictly, then we call it is a totally ordered set. Okay, but if some of the elements this relationship holds, that means they are be equal, so uh, then it is not totally ordered, it is partially ordered. So example is that in usual ordering relation, this on R or on Z is a partial ordering of that sets. In fact, it is a total ordering of the either set. This ordering of Z is the basis of proofs of by induction. Okay, the next slide. Now this is the example. Examples of uh, on Z plus declare A by B by this. Okay, A is less than equal to B by this relationship. This partial ordering of Z is different from the one in above example. Before example is there, this example. Okay, and is called ordering by divisibility. This is the divisible. A is divisible by B. It is one of the central relations in number theory. Proof about Z plus in number theory sometimes work not by induction but by starting on primes, then extending. So this is the uh, extra note that I have given it. If you find interesting, you can continue. Unlike this, the ordering of Z plus in above example, Z plus is not totally ordered by divisibility. Most pairs of the integers are not comparable under the divisibility because, for instance, 3 does not divide by 5 and 5 does not divide the 3. So the subset of powers of 2 is totally ordered under divisibility. You can check. Okay, so divisibility means A must be less than B, that is A will be divisible by B or B will be divisible by A. Here you see. Okay, it's totally ordered. Okay, next another example, set of all subgroups of a group G. These are all subgroups. For H and K belongs to S, that is H and K are subgroups of G. Declare H is less than to equal to K if H is a subset of K. Then this is also a partial ordering called ordering by inclusion. Okay, it is not a total ordering. You check it, you know the group theory, you check it. This is also not also a partial ordering. Then these are the examples of the partial ordering. Example, declare A by B by B by A. Okay, here that, as I told, this is called reverse divisibility. Okay, so this is also a here one integer is larger than another if it is a factor. Okay, so this is also a reverse divisibility. Reverse also a partial order. Then another example, let A and B be the sets. Let S be the set of functions defined on some subset of A with values in B. S be the set of functions defined on some subset of A with values in B. This subset can vary with the function. That is, the S is the set of pairs X and F, where X is contained in A and F X to B. Two elements XF and YG in S are equal when X is equal to Y and Fx is equal to Gx for all X belongs to X. We can partially order S by declaring this. When X contained in Y and G, this means G means F means G. This means G is an extension of A to a larger subset of A. There is a definition. G, this bar, not bar, this the perpendicular bar X is equal to F means G is an extension of A to a larger subset of B. Okay, let's check the second property of a partial ordering. Second property, just go back. This is the second property. Okay, this is the second property. So you have to check if this holds and this holds, then X is contained in Y and Y is contained, so X is equal to Y. Then the condition this is equal to F means G is equal to F as a functions on their common domain. So XF is equal to YG. So this is a bit hard definition. You have to remember all these lines. What does that this means? Then two elements, how it is defined. So this is bit hard, but I have given it for your larger studies. Okay. Now next thing is that is in your syllabus. You have taught it in the I told you in this first semester classes that there is well ordering principle and its applications. Well ordering principle definition: a non-empty subset of S of R is well ordered. Well ordered if every non-empty subset of S has a smallest element. That means uh, it starts from a smallest elements and go on one after another in such a way that the smallest element, then comes the next smallest, then comes the next smallest, in this way. The well ordering principle, the same set n is 1. The set of natural numbers is well ordered. Set of natural numbers means 1, it starts from 1, then comes 2, then comes 3, then comes 4, in this way. So it is a well ordered set. The following sets are also well ordered. You see, natural number union 0. So who is the least element, smallest element? 0. Next, natural number union -1 and 0. Then which one is the small element? This one. Then natural number minus this one. Then which one is the smallest element? -3, and so on. The following sets are not well ordered. R. The open interval 0 to 2 is a non-empty subset of R, but it has no smallest element because this is an open set. This is an open set. This is not a closed set. If it is closed set, then the lowest element was 0. But if it is open set. So there are possibilities that the numbers lying in the left of 0 may be there, but which one is the lowest, nobody knows. Then Z, the set of negative integers, is a non-empty set. So set Z, I must give some symbol here, uh, but with no smallest elements. Okay, these also uh, the interval 0 1, because 0 1 is a non-empty subset of this set. So uh, this one has no smallest element. A subset, remember, always you have to subset which has a smallest element. So this is well ordering principle and its application. Then division algorithm. Given A and B belongs to Z, B greater than 0, there exists a, again someone entered. Oof. So application 1. So this you have to, the division algorithm, there exists QR for which this holds. Consider the set S. It holds for S contained in N union this 0. Check it. To see S is non-empty, we can take X is equal to this, so that A minus XB is equal to A plus X mod A B greater than equal to 0. Because B is a positive integer, B is positive. So B is greater than equal to 1. Hence A is equal A plus A mod A plus B belongs to S. But the fact that A n union this is well ordered, that is, it has a least element in S, call it R, and R is equal to A minus QB for some Q. So prove that R is less than equal to B. If R is greater than equal to B, then 0 less than equal to R minus B is equal to A minus Q minus B minus B. Now see this line. So that means but with the help of well ordering principle, the division algorithm is going to be proved. Okay, this is the another proof. This division algorithm has been taught to prove in your class 11 or 12, but this is by using well ordering principle. Okay, so this is a bit new. That's why I have introduced it. And if you use this one from this definition, then you will get this one. And this is, so R minus B is less than belongs to S. So R is less than B, which contradicts R, which contradicts that R is the smallest in S. So uh, there is a least element, call it R, so which contradicts that R is the smallest. Okay, so there is no R. Again someone, so there is no R. So division algorithm which contradicts that R is the smallest element. Okay, so in this way you can prove the division algorithm. I don't think it is required for your examination purpose, but this is for your interest. This part of this class is mostly uh, mostly definition, and there is, I don't think there is no. Now to prove the principle of mathematical linear with the help of the well ordering principle. So this is also like this another one. Okay, so you can prove it by actually well ordering principle and principle of mathematical induction, they are compatible to each other. That means if you prove well ordering principle, you need principle of mathematical induction, or if you want to prove this principle of mathematical induction, then you need well ordering principle. Well ordering principle cannot be proved independently. Principle of mathematical induction cannot be proved independently. Sometimes it is called then like this axioms. Okay. So in taking about variables, now there is question is that what is ordinals? So to understand the ordinals, uh, we have to understand the what is called variables in mathematics. In mathematics, variables has different meaning, many meaning. Okay, here we see sometimes you hear variables being described as categorical. What is mean? Does it be categorical? Means uh, sometimes nominal, sometimes ordinal, sometimes interval. We define these terms and explain why they are important. Categorical or nominal. A categorical variable, sometimes called a nominal variable, is one that has two or more categories, but there is no intrinsic ordering of the categories. Now, see here a binary yes or no. Now, there is a set, the answer set of questions. Okay, the questions can be given in the form of answer yes or answer, and answer must be yes or no. Okay, so the first one may be yes, the second one may be no, the third one may be no, fourth one may be again no. Okay, in this way you can go, but in this way you can go, but there is no order. Order means something like this, that first one is yes, second one is no, third one is yes, fourth one is no. This is called order. But if there is no order, then it is called a nominal variable. Okay. Another example is that hair color is also a categorical variable having a number of categories: blonde, brown, brunette, red, etc. And again, there is no agreed way of order these from highest to the lowest. A purely nominal variable is one that simply allows you to assign categories, only categories, but you cannot clearly order the categories. Okay, if the variable has a clear ordering, then that variable would be an ordinal variable. And even in your syllabus, only this definition is give there. But there is ordinal mathematics. Ordinal mathematics, after defining the ordinal, then cardinal number comes. But I don't know who has designed this syllabus. An ordinal variable is a similar to a categorical variable. It is a categorical variable. The difference between these two is that there is a clear ordering of the categories. For example, suppose you have a variable economic status with three categories: low, medium, and high. In addition to being able to classify people into these three categories, you can order the categories as low, medium, and high. Then this, if you can categorize this, then it is a ordinal. These variables are ordinal. Now consider a variable like educational experience with values such as elementary education, elementary school graduate, high school graduate, some college, and college graduate. These also can be ordered as elementary school, high school, some college, and college graduates, even though we can order these from lowest to highest. The spacing between the values may not be the same across the levels of the, say we assign scores 1, 2, 3, and 4 to these four levels of educational experience, and we compare the difference in education between categories 1 and 2 with the difference in educational categories between categories 2 and 3, and the difference between the categories 3 and 4, so on. The difference between the categories 1 and 2, 2 is elementary and high school, is probably much bigger than the difference between categories 2 and 3, high school and St. In this example, we can order the people in level of education experience, but the size of the difference between the categories is inconsistent. Okay, size means number of people having school education, elementary education, high school, like this. uh, but the size of the because the spacing between the categories 1 and 2 is bigger than categories 2 and 3. If these categories are equally spaced, then the variables would be in the an interval variable. Okay, these are required in statistics. Now I want to show you some very simple meaning of this. Okay, suppose this is a racing competition. You see, this is the first one, and at the end point. So first, second, third, fourth, fifth, sixth, seventh, eighth, ninth, tenth. So this set is a ordinal set because each one has some order. He is in the first position, he is in the second position, he is in the third position. So ordinal set has, each element has some order. Okay, that means place value. That is place value. Each element has some place value. But you see, the this is the picture. Then cardinal numbers, first one is 1, second 2, third, these are the cardinal numbers. But ordinal numbers, first, second, third, fourth, in this way. Okay, so this is the positional value. These are the positional value. So ordinal numbers, that each number have some positional value, as well as the total number of the sets discarding the total number in the set. So this is the ordinal number. So this is what I intended to complete the first part of the syllabus, but I am not satisfied with these cardinal numbers. Still, I am going to give you some assignment in the next class on this. I am showing you the others one also. Let us see. Can you see this one? Okay, this has been done, but I think this is the treatment is rather difficult because you are third year students. Okay, so these sums are very important for the examinations. Then proof of this one also very important for the Cantor theorem is also very important for examination. Then this is also very important for the examination. Now this slide I have not explained because it is bit hard, so you can omit this side. I shall give you the uh, required sums in the next classes, and in the next class I shall start with the definition of the topology. Okay, so from the Saturday I will give you the full notes. Today I am sending you this part of the way, mostly calm this part of this today's lecture. uh, it is based on the definitions and understanding. If you want to understand, read more, today I am sending you some good articles on this topic. Okay, today I'll send. So I want to uh, before that I want to finish it today, because uh, if there is any question on Schroeder-Bernstein theorem or Cantor theorem, you can post it uh, in my WhatsApp number. I can answer it, but one problem is that what type of questions will come or what type of questions may be asked is not known to you at all, because you are the first sixth sem batch. So I think this part of this program is bit difficult one, because it is on the fundamental issues of the mathematics. As for example, Hilbert posed Hilbert posed this 23 problems in the beginning of this century, and the first problem was this. continuum hypothesis. Okay, to prove it is a challenge, and some mathematicians tells that it took 1,000 years to prove, another 1,000 years to prove this continuum hypothesis. Continuum hypothesis is still a mystery in mathematics. So there are 23 such problems. Some of these problems have been solved, but some are not solved. So here, these issues are fundamental in mathematics. So this is a bit hard. I do admit that this is a bit hard. So today, this much is enough for your first part, and tomorrow I shall start the second part. Okay, then you can go now. I'm just stopping the recordings. Okay.